Hey guys, so this video here is still on kinetics. We've gone away with types of reaction rates, and now we're kind of putting it all together and talking about a small concept called half-life. Now, I promise this video isn't going to be as long as the differential rate law and the integrated rate law, so it should be pretty short and sweet to be able to look at that. So let's say that I have here a concentration versus time graph, and you see clearly here that we have a curve. Well, we don't know what the order is of this reaction, but we can, now that we've gone through integrated rate law, we can probably figure out which order it's not. Because this is concentration versus time, what order is that associated with? It's associated with zero order. And because it is a curve, it is not a straight line, what that tells me that it is not a zero order reaction. It might be first order, it might be second order, heck, I don't know, but we know it's not zero order. So what we can look at here is we can determine a couple of things if we have a concentration versus time. We can determine the half-life. So first, let's explain what half-life is. Half-life is the amount of time that it takes for half of that substance to disappear. So we have our reactant decreasing in concentration over time, right? So basically, we're trying to figure out how much time it takes for half of this stuff to disappear. Pretty simple. So all I have to do is look at this graph and figure it out. We started out with 1 molar for my concentration. So how much is half of that? Well, half of 1 is 0.5. So how long did it take for this reaction to have 0.5 disappear? Well, that would be 3 seconds. All I have to do is look at my graph. So that's pretty easy, right? Now, there's a next question. What is the molar concentration of element Q? So I guess we're working with element Q here. After a second half-life has elapsed. Well, if one half-life is 3 minutes, and we just determined that, how many would 2 half-lives be? It would be 6 minutes. It's just 3 times 2 is equal to 6. So I would have to figure out what is my concentration in 6 minutes. So it's in between 0.2 and 0.3. So we can say it's somewhere around 0.25 molar for our answer there. Pretty simple. All you have to do is be able to read a freaking graph. Now, number 4. At what time has 75% of the original sample decayed? This is a little bit tricky. If 75% decays, that means it goes away. 75% of it has disappeared. How much of that percentage has remained? Well, if 75% has disappeared, that means that 25% remains. So I have to figure out what 25% of 1 is. Now, the reason why I have to not look at 75% disappear, I want to figure out what's remaining, is because each one of these dots, that is representing the concentration that is remaining over that time. So, 75% has gone away, 25% remains, 25% of 1 is 0.25. So my answer there would be 6. So the way that you apply half-life is really just a logical approach when you're working with the graph. Simple, very easy questions to be able to get. Now, the next concept is first order half-life equation. When we are working with half-life, we are only working with first order reactions. There are half-lives for zero order reactions. There are half-lives for second order reactions, but we're only looking for first order reactions. Why? I don't know. AP just said let's do it, okay? So there is a way to find half-life for zero order and second order, but for AP standards, we're only going to deal with first order. Now, I believe that the equation for first order half-life is on your equation sheet. So, that equation is t to the 1/2, that's how we represent half-life, t to the 1/2, is equal to 0.693. It is a constant. It's been derived from another formula to be able to figure out what this is, over k. Now this k, remember, is your rate constant. So when do I apply the graph method, the logical method? When do I apply this? Well, the only time when you really have to apply this equation is if you're trying to determine a half-life and you're given a k value. So anytime you're given rate constant, you're not given that graph, you will have to use this equation for your approach. So I've seen a free response question. It was a 2014 question. And tons of students in the nation got the question wrong. So I want to just point it out to you. Here are some other pieces of information you need to know. This is definitely the equation for a first order reaction only. All right, we're not going to get into the half-life equation for 0 and second order at all. You can look up that on your own time if you'd like. Now, what do you see is in this equation? You have 0.693, which is a constant. Well, the only thing that is not a constant is K. So, concentration is not in this equation. So what that means is that concentration does not affect your half-life. Very important topic there. There is something, however, that does affect my half-life, and that would be my K, my rate constant. Now, they're not going to directly say, hey, your rate constant is changing. Instead, they're going to say temperature. If you remember from our differential rate law video, we were talking and introducing about K, the rate constant. K is temperature dependent. So the value of K changes when the temperature changes. So since K is temperature dependent, then that means half-life can change for temperature as well. So let me show you where this is implemented. 2014, question 7. This is the data that students were given. So they had cis-butene, trans-butene, and it doesn't really matter what this is. What matters is the information that was given to you. Well, what you were given was initial pressures. Pressure and concentration pretty much goes hand in hand. You had different volumes, you had different temperatures, and you had half-life. So the question is, look at part A. The reaction is first order. Explain how the data in the table are consistent with first order reaction. Students all across the nation were trying to apply differential rate law. So that's where you do like the table logic, right? So like as my concentration or my pressure doubles, then my time is staying the same or my time is doubling as well. Well, this is not differential rate law data at all. If you remember from that video, differential rate law data is concentration versus rate. We don't have rate anywhere in this data table. So they could not use the differential rate law approach. If they tried, honestly, you would say it would go 300 to 600, that's doubled, but that stays the same. So wait, it's not first order, it's zero order, which totally contradicts what the statement says. Instead, what they had to talk about was that since they knew that the half-life equation, let me get that back up here. Since the half-life equation is 0.693 over K, a concentration does not affect half-life, but a temperature change does. So let's go back and look at this data, Remember, a concentration change does not affect half-life. Well, here I'm changing pressure, which for gases is essentially concentration, and my half-life stays the same. But I keep concentration the same. Look at trial number 3 and 4. I keep concentration, or in this case, pressure the same, and my temperature is changing. You see, my temperature didn't change in trial 1 through 3, but my temperature is changing 3 to 4, and guess what else changes? My half-life. So make sure you know how to apply this equation. Yes, how to calculate half-life. Yes, but most importantly, that this is the equation for first order reactions only. Okay? So that's something very important to know. I'm going to pause this and get some things ready for our next part. All right, sorry about that. So what we want to do now is refer to multiple choice half-life questions. So how can they ask this kind of stuff in multiple choice? Well, one, they can give us the graph approach. 2, they could give us this first order half-life equation, so they could give us a K value. We might have to figure out a half-life. Or they can do just a wording and have us figure out half-lives and percent remain and something like that. So I made 3 multiple choice type questions. Now I know that it's not a multiple choice format, and just kind of shorthand it. But we're going to go through these 3 real quick and figure out how to work through them. So let's say we have the first question here. We know that half-life is equal to 5 minutes for whatever reactant that this is. And what we want to figure out is how long, what is the time for 12.5% of that stuff to remain. So the way I like to work this out is basically just reasoning through it, but I like to start with, if we're working with percentages, I want to work with all of it, right? So I'm starting out with 100%. Now I've got to figure out, well, how many times do I need to go through a half-life for 12.5% to remain? So half-life means I'm cutting that stuff in half. So if I go through 1 half-life, that's what this arrow is representing, I have 50% remain. Well, if I have 50% remain and I go through another half-life, then I now have 25% remain. If I have 25% there and I go through another half-life, now I have 12.5% remain. So you see what you're doing is cutting in half every single time. You're breaking it down, cutting in half, cutting in half, cutting in half. Now, some people like to say, oh, well, that's 1, 2, 3, 4. That's not 4 half-lives. The half-lives that I count are the transitions. So this is 1 half-life, 2 half-lives, 3 half-lives have taken place. Now, if 1 half-life is 5 minutes, how many would 3 half-lives be? Well, that would just be 3 times 5, which is equal to 15. What's the time unit we're working with? We're working with minutes. So you see how I'm just reasoning through these questions. So this is how I would answer number 1. Now let's look at number 2. We want to figure out the half-life now. So what is the half-life if 20 minutes is the time it takes for 75% of something to disappear? So remember when we were counting all of these values here? All of these values are the values that remain. So if I have 75% disappear, how much remains? Well, that would be 25%, right? So we want to figure out how many half-lives it takes to have 25% remain. So let's start at 100%. 1 half-life is 50%. 2 half-lives. Remember, I'm cutting this value in half. So half of 50% is 25%. And I've gotten to my goal, right? 25% remains. So the question is, how many half-lives did it take to get there? Well, I have 1 half-life, 2 half-lives. So if 2 half-lives is equal to 20 minutes, how much would 1 half-life be? Well, it would just be 20 divided by 2. So that's equal to 10 minutes. And that would be my answer there. So you see how I'm just reasoning through this stuff. Now let's look at another format of the same question. Let's say we know that 1 half-life is equal to 2 minutes. How much would remain if 8 minutes has passed? So we can look at a percentage here. So if I know that 8 minutes has passed, all right, so how many half-lives is that going to be if I have 8 minutes passed? Well, what I'm doing here is I'm saying how many half-lives times 2 is equal to 8. Well, that amount of half-lives is equal to 4 half-lives has taken place, right? So I have to figure out what percentage remains after 4 half-lives take place. So I have 100% to start off with. 1 half-life would be 50%. 2 half-lives would be 25%. 3 half-lives would be 12.5%. And 4 half-lives would be half of 12.5, which would be 6.25%. So this, again, is the amount that remains. What if it asked how much would disappear? Well, if they asked how much would disappear, that would just be this percentage subtracted from 100. So 6.25% remains, and that means that 93.75% has disappeared or reacted, or however you want to phrase that. So 93.75% disappears, 6.25% remains. So I hope this is helpful. I hope you guys grasp onto this like multiple choice concept pretty easily. This is a very easy concept to get some points with as long as you know how to do it properly. If you have any questions, just come by and ask me and I'll help you out the best I can. See you in class.